Welcome Engineering Statics. This is ENGR ampersand 214 at Bellingham Technical College. The topic of today's lecture is friction. And from the standpoint of statics and our equilibrium analysis, friction gives us effectively another relationship that we can use to solve equilibrium analysis, to understand forces and moments necessary to keep things in static equilibrium. But to deploy friction properly, we have to take a little bit of a dive back into our physics. So we're going to start there and just start with a definition of what friction is from our standpoint of mechanical interaction between two bodies. Friction definitely is in the realm of contact forces, so we'll only be looking at friction when there's actual physical contact between two rigid bodies. So here's an example. We have body B1 and B2 and they're contacting at a point or over an area. If we draw a normal to their point of contact, we can define a tangent plane that they might want to move along, and so friction is going to be operating in that plane. So if we look at just B1 and we take B2 away, we can represent the action of B2 on B1 with good old Newton's third law, and we're gonna say the force with which B2 is pushing on B1 is N, and this is known as the normal force, and it's called normal because it's normal to the plane on which these two bodies might slide relative to one another. So not very creative. N for normal force. And so friction will always oppose the direction at which we are trying to move the bodies, or the bodies are trying to move relative to one another. So if B1 is attempting to move in the direction of this dotted line, friction force is going to oppose that motion in a direction that is collinear and an opposite orientation. So that's pretty much a repeat of what we might have learned from physics, and if you didn't learn it in physics, you know it now. Okay, so let's take a look at the limitations of friction in terms of our overall equilibrium analysis, because what most physics studies don't take into account, and we will certainly be using, is moment. And let's look at how friction operates when we have to consider equilibrium, including no rotation. So we're going to start with a box, and it's sitting on a surface, and that surface can push back against it to keep it from accelerating. This box has a center of mass somewhere in the middle, and it's got a weight that is given in gravity, that's its mass times the gravitational acceleration. So the normal force in this case is simply the weight, where sum of the forces in the y is 0. Now if we come over and we start pushing on this box from the side, I'm going to try to get this to the center, and it's not going to let me. So same box, same weight. We're gonna apply a horizontal force P to this box that is in line with point A. Sorry, draw a line here. So there's the line of the action of force P goes through point A. So we have the weight coming down. So that force is going to cause the box to want to slide across the floor. Now, this is statics. We're assuming that we're going to have our frictional force is going to keep us from moving, so we stay in static equilibrium, but now we have a force, and we know that friction is going to have to oppose it. Okay, so our imminent motion, or our direction of motion that the body would want to have, is towards the right, so friction is going to work towards the left, opposite. Okay, we could write equations of equilibrium at this point, so we could say the sum of the forces in the x is P minus F if we've made our I hat direction to the right and our J hat direction positive upwards, and we could say that our weight of the box is again being opposed by our normal force. So that's a pretty simple sum of the forces in the y. But if we want to look at moment, we're going to find that there's something different about the location of our normal force resultant. And in reality, we're going to take a little step back here, and we're going to go back to our static box. This is something that not all of you will get to, but if you take mechanics of materials and you go on in your studies, something that you will want to be aware of is that gravitational force, remember, is a distributed force, right? So, it's acting over the whole volume of this box, or its entire mass. So it's operating in 3D. Likewise, the normal force is also a distributed load, except it's a distributed support, I guess we could call it. And so it's not just acting at one point, it's acting all along the bottom of the box. So when we draw the normal force in line with the force of the weight, there, I'm drawing my line between the two, what we're actually doing is showing the location of the force resultants. That weight that's acting at the center of mass of the box is actually a resultant force. So what we've done is we've integrated our gravitational force over the entire box, maybe taking into account its density, uniform or not. The same thing with the normal force. We went ahead and we did a force distribution resultant, just like we did earlier in the class with applied weight loads on beams, and we got a total normal force and an appropriate location for it. In this case, it had to be collinear with the weight to prevent a moment. Okay, so when we're looking at weight, and especially when we're looking at normal force, just keep in the back of your mind, this is a force resultant that's representing the action of a distributed load, which may or may not be uniform. And that's effectively what we're going to find over here, that in this case, over on the static side, the left side, or no horizontal force side, excuse me, our normal force was uniform. It was pushing up with the same strength all the way across the box. What we're going to find in reality when we come over here is the normal force distribution actually is non-uniform, and so it'll have something like this. So our resultant, of course, is going to shift over towards the right versus where it was when we didn't have any horizontal load. So I'll get rid of my scribblings here and we'll continue. So N here is our normal force resultant, and now it's not acting right in line with the weight. And the reason it's not is it has to shift over, or the normal force distribution has to become non-uniform and actually become stronger, have a greater force per unit length as we get closer to this bottom right corner. And all that's doing is ensuring that the moment due to F and N about point A balance. So we could write a sum of the moments equation around point A and do R cross F. So we could define a radius vector from A down to our friction force, R cross F, and we could get a moment that will be negative going into the paper due to the friction, and we can define a line of force of our normal force up here and do a radius vector to it and show that that has a moment going out of the paper, and we can set them equal to one another to keep this box from rotating. Okay, so here's our total equations of equilibrium. Some of the forces in the X, the horizontal forces being opposed by friction, or the box would move. The normal force coming up from the ground, the total magnitude of that resultant has to equal the weight. However it's distributed, it has to all total up to the weight. And here's our moment expression. We've got the distance, the perpendicular distance of application of friction force at H up here, causing a negative moment into the paper, and then we have our normal force acting at this offset from the center, delta. That's the Greek lowercase delta, positive. So from this expression we can say the greater the friction force, the more the normal force resultant shifts right. So this delta increases. So we can look at basically some corner of the box, pun intended, conditions. We can look at cases where the box is just ready to slip across the paper but stay upright, And we can look at what would happen when the box is ready to topple over by pivoting around this bottom right-hand point. So we're going to explore those two options because those give us a very important criteria, which is the tilt onset. And we'll also look at friction angle, so another way of expressing our coefficients of friction. Okay, before we do that, we have to introduce a very important concept that's probably, again, familiar from physics, which is imminent slip. If the box isn't anywhere close to slipping, we really can't say anything about the magnitude of the friction force other than what we can get indirectly from our conditions of equilibrium. But if the box is just about to slip, this is called imminent slip or slipping point, we can relate the maximum value that the friction force can give us to a coefficient, a dimensionless coefficient, and this is dimensionless, and the normal force, or the magnitude of the normal force resultant in this case. And that coefficient is called the coefficient of static friction. This is static, so it's imminent slip. It hasn't slipped yet, it's not moving, so it's static. And this is known as mu sub s, Greek letter mu with an s lower coefficient, meaning static. So this is basically our additional relationship that friction relations give us that we're going to add to our conditions of equilibrium and help us solve problems where friction is involved. We will pull this out if and only if we know the system is at imminent slip. So look for words in problem descriptions or out in the field in some kind of write-up that indicate maximum criteria for no slip. You're going to have to hear the word slip and some kind of language that indicates you're right at the edge where something is ready to move. Before that, if you're not at that point, you can't apply this relationship. But typically friction problems involve what do we have to do to not make something move, so generally it will apply. But remember that it has to be at that point. For those of you who will be going on to dynamics, please be aware there are different coefficients of friction depending on whether you're moving or not. There is a mu sub k, a coefficient of kinetic friction, and it's almost always less than that for the static. So if something's already sliding and moving and you're looking at the frictional resistance to solve a dynamics problem, looking at force necessary to achieve an acceleration, you'll use mu sub k, not mu sub s. And generally speaking, the relationship between mu sub s and mu sub k, it can be defined in terms of how that friction force is going to respond as we increase the shear forces applied to a body to make it move. So if we're measuring this in a lab, say, and we're measuring frictional force in terms of resistance to visible measurable slip with increasing applied force, you'd see if we were increasing our applied force linearly with time, say, you'd look at your friction force would kind of go up linearly. It would reach a maximum, and this is our imminent slip, and then your body would start to slip. And if you were to measure friction force, it would decrease, and then it would approach a constant, asymptotically. And so that asymptotic level would correspond to mu sub k times your normal force, and your peak is mu sub s. So that's how those two relate. In statics, we will of course be using mu sub s, as we will not be letting anything accelerate. There are some special relationships that we can define with that definition of imminent slip for friction force and just our plain old equations of equilibrium, and these are used in geotechnical applications quite a bit, and that is called the friction angle, and it's literally another way of describing the static coefficient of friction. And what it means is basically the maximum angle at which you could tilt something before it would begin to slide down a surface. So if you're worried about some big block of rock sliding down maybe a geological contact towards something parked in your parking lot, that becomes very important. It's actually a consideration in highway design steep terrain. So we can define that just by drawing an FBD of a little block on a theoretical slope. We've got a slope angle of theta. We've got our normal force coming up out of the surface. The block's going to try to slide down the slope, so friction's going to be acting on the block upwards, and of course weight's straight down. So if we resolve all of our forces and we write things in terms of forces perpendicular to the slope and parallel to the slope, we end up getting this upper equation of forces perpendicular, or excuse me, parallel. Friction's parallel and being opposed by portion of the weight, and then we've got the larger portion of the weight typically being opposed by the normal force. At impending slip, we can replace F by our nice mu sub s times n and get this. We can get rid of one variable basically, and so now we have basically just normal force, mu sub s, and our slope angle. If it turns out if we rearrange these equations and we solve for our coefficient of static friction in terms of that slope angle, do a little rearranging, we get this expression. Everything else ends up canceling out, and we're left with an expression of our coefficient of static friction in terms of only the angle, with a couple of trig functions. So as we all know, sine over cosine is tangent, so we can say that mu sub s, or the coefficient of static friction, is equal to the tangent of the slope angle at which slip is imminent for the block that's going to slide down it. So this angle is sometimes known as the angle of repose or the friction angle, and it is literally another way of expressing mu sub s. So tangent of mu sub s is a way of expressing a coefficient. So somebody can say, what's your coefficient of static friction on that ramp? Or they can say the tangent of the friction angle is, and give a number. Notice they're both unitless. So that's an important consideration. That's a good way of telling you that you didn't make a math error. So as an example, we're going to do a unitless, or a numberless, excuse me. There's units contained within the variables. We're going to do a numberless example, and we're going to kind of derive the toppling criteria and sliding criteria for a block that is we're trying to move, or for which we're applying a force that's opposed by friction. So we've got our crate again. It's got uniform density, and it's got a width of b, and we're applying some horizontal force P, and we're applying it at some height h. Now just intuitively, most of us could probably think, hey, if you want to push this crate along and you don't want it to topple, you're probably going to want to apply P down near the bottom. And if you want to topple it over, like roll it over to maybe see what's on the bottom side, you're going to apply P up high. And that intuitive thinking most of us probably have is basically an unconscious application of equilibrium based on moment about this lower point. So that's what we're all intuitively doing. So we're going to kind of do that a little bit more rigorously and derive ourselves some nice equations for how wide the box has to be and where we're going to apply force for what mu sub s on this floor, where we could slide the box, and at what point, given dimensions and height of application, are we going to turn the box over. Usually we just want to slide it. So if you need to move something, you're trying to slide it across the floor, how do you do it? What are the limits given the geometry before it's going to start to roll? Okay, so we're gonna do a general FBD of this and start this derivation. We're going to slap a coordinate system on. So x, or I hat, increases to the right, and y increases upwards towards the top of the paper. So I've defined my point of application of P goes through point A again, same kind of nomenclature. It's at distance h up from my rigid sliding surface, and A is at B over 2, the box is width B. I've got a frictional force opposing that P, and I've got a normal force resultant acting at some delta somewhere between the center of the box and going through the line going through the center of mass and this bottom corner. So great, I can use this FBD and write equations of equilibrium. So I'm going to start with sum of the forces in the x. I got P in the positive direction, and I've got F in the negative. So P minus F. I'm going to assume at this point imminent sliding. So I can replace F with mu sub s times n, and now I have a relationship between P, mu sub s, and n up here. So I'm going to turn my attention to the sum of the forces in the y. I've got the weight, mg, being opposed by the normal force, the magnitude of the normal force resultant, so negative mg plus n. So now if I wanted to, I could replace this n up here with an mg. Might be useful later. And I'm going to take the sum of the moments about point A, not the bottom corner. I'm going to take it about A. So P can't cause a moment about A, and neither can the weight, because they're both their lines of action pass through A. But F certainly can, and N certainly can. So using my definition of moments, I've got H times F causing a moment into the paper, and delta times N causing moment out of the paper. And if I don't want the box to rotate, those two have to add to 0. So there I go. So I can drop in my expression for friction, given that we're at imminent sliding. I can substitute that in for F. And now I have N in both terms, so these cancel. And I'm left with an expression relating delta, the offset distance for the normal force resultant, and the height at which my horizontal force is being applied, and mu sub s. Okay, well, that tells me something. So now let's think about kind of what are my maximum constraints. Delta is kind of a funky thing. I can't really measure it. It isn't like I'm applying a force directly at delta. That's basically the location of a distributed force resultant. So let's think about how big and how small that can be, and what our limits are. So we can look at the maximum possible moment that the normal force resultant can apply. Now that's going to apply to toppling, right? So eventually, if I increase P more and more and more, I'm going to basically have to keep increasing F, or the box is going to slide. And so, but as I increase P and I increase F, I'm going to have to keep, N's not going to increase. It's always going to be equal to mg, so it's just going to have to keep creeping out further and further to the right to increase its moment arm, to increase its effective torque around A. So the maximum level, the maximum value for delta is B over 2, because N is eventually going to coincide with the corner of the box. It can't go any further. So that's effectively our limiting criteria for toppling. So this is the biggest moment that we can get from that normal force resultant. So delta equals B over 2, and that's as big as we can get. So we can define a toppling criteria by putting in B over 2 for delta. So if we continue to do that, and we relate equations together, we can say our slipping criteria effectively for P, maximum P, is going to be mu sub s times ng, and that came by just substituting in mg for n up in our two force equations. So that's our slipping criteria. P can't get any bigger than mg times mu. And if we want to prevent toppling, it turns out we get the same thing. And the only difference in the two is the distance over which our delta is defined. So we can throw that in. If we want to define a toppling criteria, so a geometry, some kind of relationship between the box width, the height at which we're going to push on the box, and our coefficient of friction along the bottom of the box, we just basically take these relationships and these, and our earlier definition of delta, and put them together, especially with a toppling, and solve for mu sub s in terms of h and b, and get mu sub s equal to b over 2 times h. So if you know your coefficient of friction with the floor, and you know you have to push at a certain height because maybe you can't bend over too far, or that's where the forklift can push against it without punching a hole through something, you know how wide your box has to be for it to not topple over. So that was just some algebraic relationships. But the key here was to know the relationship between mu sub s and mg for no slip, and then to recognize this limit on how much normal force that or how much moment that the normal force resultant could apply. Can't apply any more than n times b over 2. And so it's that relationship that gave us this. So that can be handy. Not necessarily a lot of questions, but certainly if you have to move things, that's important if you don't want them to topple over. Okay, we're going to work through a few example problems of just generalized equilibrium analysis, where rather than having a frictionless situation, we have friction, and generally friction is a major component of the problem. So we're going to start with this one. We've got some kind of cylinder, and it's imagine that it's got two different radii, so it's kind of an axis symmetric part, and it's sticking out of the paper. And so it's got a center here at C, and then it's got some way to attach some kind of cable, fixed length cable here, right above C, you know, kind of like at 12 o'clock, say. And this is fixed. It's like, you know, bolted on or something like that. So basically there's nothing holding this kind of a cylinder, like a can or you know, an axle or something, to this slope other than friction. So if there was no friction here, this whole thing could maybe rotate around that point and move such that it was in a different configuration. So the aim of the problem is to find what is the maximum angle at which we're going to start getting slip, and we're going to find that in terms of all of the variable expressions in the problem, so we don't have to do any calculations. It's a lot easier. Okay, so at what point does slipping start? And we've been given a definition for coefficient of static friction between the cylinder and the ramp of mu sub s. It's something, some dimensionless something. So one of the challenges with friction is, in order to get the direction of the friction angle correct, you have to envision what is the direction of imminent motion that we're kind of trying to prevent, in this case, to keep things in static equilibrium. Friction vectors have to be drawn in the correct direction. They won't self-rectify like some of the force directions we've seen in earlier equilibrium analysis. So that's probably the biggest challenge. So we have to kind of think in terms of which direction is something going to slide, given the forces that are being applied. So in this case, the cylinder is going to try to rotate such that this point comes down here, and then this point slides over there, and the center displaces over here. Okay, so if we're looking at an FBD of the cylinder is going to try to slide to the left. Basically, it's going to try to rotate clockwise. So if we come down and look at our FBD, the friction force is going to be tangent to that point. It's going to be going kind of pushing it in a counterclockwise direction. So we know that. So everything else is pretty easy. The rest of it is just geometry. So we know we have the tension in the cable at our point A, and we know that the cable, geometrically the cable is parallel to our ramp. So we know the cable's direction of pull. We know its vector direction is also theta, so it's the same as the ramp. We know that the weight is going straight down, and we can resolve that into components parallel and perpendicular to the ramp just using geometry, and it's the same angle theta. And we've got a normal force pushing up against the cylinder by the ramp, and that's keeping the cylinder from like sinking down into the ramp. So that's our normal force. And so we know all of those angles. So now it's a matter of, do we have enough equations of equilibrium to solve for what we needed to? And so we'll review. We want to solve for theta in terms of everything else. So we can just go ahead and excuse me, start writing our equations of equilibrium and then isolate theta. It's actually a little bit easier. So in this case, we're not going to do sum of the forces in the x and the y. We're going to do the sum of the forces in the tangent and normal direction relative to the ramp. It just makes it a lot easier. So here's our coordinate system. So we have our tangent unit vector and a normal unit vector, and these are of course orthogonal, and they're at an angle theta to our kind of up and horizontal and vertical coordinate axes. So the sum of the forces in the tangential direction, so we've got the rope tension pulling upslope, we've got friction pulling upslope, and we've got the sign of the weight, the tangential portion of the weight pulling downslope. And so looking in the normal to the slope direction, we have the normal force pushing up, and then that's being opposed by the normal portion of the weight, so the cosine theta portion. Okay, so how many unknowns do we have in these two? We have theta, t, n, and f basically, and only two equations. I should have added f to that. And so we're definitely going to need a moment equation. Actually, we have 4 unknowns. I should say 4. So we're going to have to drop in. We're going to have to invoke an imminent slip to replace f. I was getting ahead of myself when I wrote 3 equations. I was already envisioning myself putting this in the imminent slip criteria. That's why I came up with 3, and because I'd already planned to replace f with a term that included n. But even if I did that, I've still got 3 variables and only 2 equations. So I'm going to have to invoke a moment equation to give me another one to be statically determinate and then express theta in terms of everything else. So I got to pick a point that I want to rotate about, and I decided to pick the sum of the moments about A, so the connection point of the cable. So that means my moment equation is going to include is not going to include t. It'll include theta and n, and so I'm going to have to do some back substitution. I won't necessarily get it directly. Okay, so I eradicated t. So now it's all down to geometry. So this is another sketch of the problem. So here's my main radius that I was given. Here's point A, and the nice thing is the normal force is on a line of action that goes through A, which is handy. And then the friction force is normal to a line of action through A. So basically all I need is this little r plus 1 big R times friction force is the moment due to the friction force. And we can look at what other things, so that's this term. And I can look at what other things can cause a moment about A, and I need to look at a portion of the weight force. So here's the weight going vertically downward, and the normal portion of the weight force here isn't going to produce a moment about A, but the downslope portion will. So it's acting at the center of mass, and so I have my mg sine theta acting at little r. This is little r between A and the center of mass. So that's this one. So if I solve for F, I get r mg sine theta over little r, and from the moment equation, and now I can say at the point of slip, F equals mu s times n, and put these equal, so I can write the normal force in terms of all of the different givens. And then I can go back up to my equations of equilibrium and get another expression for normal force, basically, which was mg cosine theta at an angle of maximum slip. So I can go back up here and get n in terms of the stuff we want to know. So this is n at a normal force at imminent slip. So now I've replaced my thetas with theta at imminent slip, which is what I did the minute I invoked this. So now rearrange terms. And what did we want? We wanted an expression for theta in terms of everything else. So basically I grab all the terms with theta in it and stick it over on the left and divide everything else to the other side and end up with a sine over a cosine. So I can express in terms of tan theta, which is good enough, is equal to coefficient of static friction times the ratio of r plus big over little r. So this was basically just some geometry and application of conditions of equilibrium, and the main benefit was when we invoked moment. That allowed us to pull in all the relationships we needed. Okay. So, a warning, friction force must be oriented opposite to the direction of impending motion on the FBD, or you will get the wrong answer. Okay, so let's go on to another example where that is really not necessarily obvious. And this is a good practice in envisioning imminent slipping direction. So we're given a couple of blocks, and we're relying on friction to oppose this horizontal force. So we've got one block B2, and it's making a contact angle with its supporting block of 20 degrees to the horizontal. It's got some friction with the wall behind it. It's got some friction with the block underneath it. And the base block is sitting on a surface that has more friction. And we're pushing over to the side with a horizontal force P. We have weights of the blocks. P is directed horizontally. And somebody wants to know, how hard do we have to push for onset of slippage of B2 upwards? So because of this angle, as we push block 1 to the left, we're going to be basically giving an upward force on B2, and at what point does B2 just barely want to start sliding up? And that is not necessarily going to be the same answer for maybe imminent slip of block B1. So we're going to, the imminent slip is going to be defined in terms of upward motion of B2. Okay, so let's start with B2, since that's what we're basically defining the problem around. So here is an FBD of B2, and there's a lot of coefficients now. So we're going to have normal forces and frictional forces associated with every different surface. And as we go from one FBD to the other, we're going to invoke Newton's third law again and make sure that things are equal and opposite. So we're going to look at, here's our block B2. It's got a weight that points downwards, and we can resolve that weight into normal and tangential with our 20-degree slope between this block and B1. We've got a normal force pushing outward from the wall. We'll call that N1, and if we're looking at the of B2 sliding upwards, we're looking at imminent slip going up. By definition, the wall friction force is going to be going down. So the subscript 1 is referring to the wall. Subscript 2 is referring to the other block, the opposing surface. So we can write some equations of equilibrium. So we can say sum of the forces in the x are going to be N1. We're defining positive horizontal as being towards the right, positive verticals towards the top of the page. So we've got sum of the forces in the x direction, N1 plus, and we're going to have the horizontal component of F2, which is going to have a cosine 20 degrees going in the negative direction, and we've got a little horizontal component of N2 also going in the negative direction. So 1, 2, 3 unknowns. We can define sum of the forces in the y vertically being 0. So we've got the vertical component of N2 taking cosine of 20 degrees. We've got the vertical component of F2 going downwards, sine 20 degrees. We're going to have all of F1, little f1, because it's all going down. And we have the weight. So when we're talking about the sum of the forces in the y, all of the weight is in the y. So, okay, great. So now we got a second equation, but we also introduced another, unfortunately, another unknown. So now we have 1, 2, 3, 4 unknowns, 2 equations. So we can get rid of a couple of these by invoking imminent slip. So we're going to say at imminent slip, everything's ready to move, so I can drop in my normal forces for each surface, which are not going to be the same, and my coefficients of static friction for each surface, which happen to not be the same either. So that basically got rid of 2 variables. So, or you could say I introduced 2 more equations. So now effectively I have 4 equations and 4 unknowns, and so I can solve for N1, N2, and F1 and F2 at this point. I can get all of them out of this FBD. Okay, so that's good because I need to know F2 and N2 to apply them to my next FBD, because it's the FBD on the bottom block that's going to give me P. Right now P isn't anywhere around here, and that's what I wanted. But I have to start with the upper block because that's where my imminent slip criteria is applied. So I crank through some math and use my 4 equations and 4 unknowns, and I get my n's in pounds with the orientation shown on the FBD. So they're positive as shown on the FBD. So basically the bottom block is pushing upward. So let's remember that when we go to the next FBD, that N2 is going to be pushing downwards on it. And of course, since I have the N's and the mu's, I can also get the F's as needed. Okay, so I can go ahead and look at the FBD of block 1. So I'm going to carry over equal and opposite here of N2 and F2. So we can take a minute here, and this is maybe where a little bit of intuition is necessary. When we're looking at friction that opposes the imminent motion, we've already defined we want to look at imminent slip of this block upwards. So we know F1 is downwards. That's pretty obvious. What we need to do next, though, is look at which direction would we need F2 to be in for the corresponding situation, given which way block B2 would be sliding relative to B1. So basically, if we go up to our other diagram, as we push block B1 to the left, B2 is effectively sliding to the right relative to B1, a little bit of relative reference frames. And so effectively B1 would be moving horizontally from the standpoint of this plane, even though it's probably not going to. So F2 was drawn to the left for the same reason that F1 was drawn downwards. So of course we do equal and opposite when we go down to our block 1 FBD. So we got our 50-pound downward weight force, we got our horizontal force P that we're trying to solve for, and we've introduced two more variables. So now we have a normal force from the floor acting somewhere, and of course we have friction opposing the direction that we know we would have to move B1 to move B2 upwards. So that's why F3 is being oriented from left to right. So we can count up our equations and unknowns. P is an unknown, obviously. N3 is not known. It's definitely not just equal to the weight force because we got a whole lot of N2 pushing downwards coming from block B2, and we don't know F3. Lucky for us, we know N2 and F2 because we solved that with the earlier FBD. So in equations of equilibrium. So we're going to carry our solve values for N2 and F2 down here, and then we're going to write equations of equilibrium, and we'll be left with just 1, 2, 3 unknowns, and we should be able to write 3 equations of equilibrium, sum of the forces in the x, which we have up here, F2 cosine 20 plus F3 minus P plus the horizontal component, this one of N2 equals 0, and then we've got our sum of the forces in the vertical direction. So we're going to have the vertical component of F2, we're going to have the vertical component of N2, all of N3, and the weight of the block. Okay, so that's 2 equations. We can slap in imminent slip, which relates F3 and N2, and the nice thing is we didn't have to write a moment equation. We got our third equation by invoking imminent slip, so that made it much easier. So now we have the right number of equations and unknowns, and we just turn the algebra crank and get our answer, 289 pounds. Okay, we're going to end the lecture here and pick up with our second and very important application of friction in the derivation and application of the capstan equation. So any of you who are working with cables or rope or anything flexible, be aware that one of the main ways that we secure flexible tension members is through friction. Because it's not always, in fact, it's usually not practical to find something that can literally grab onto the end of a rope. It's very complicated fastening those. So quite often we'll rely on friction with a round mandrel to transfer tension incrementally with wraps to the mandrel itself. So this is an example of load attenuation. Attenuation is a concept that you use quite often in engineering, everything from electrical energy and signals to mechanical energy in the form of tension. So we will go through a derivation, and we're going to have to pull out our calculus tools to do that. So we'll be having to use an incremental element, put it in equilibrium, and then we'll use some mathematical steps to get us a very easy to use equation that we'll then deploy in some equilibrium examples. So stay tuned next for that.